Continue our examination of the light. We left off with colors, and I was talking about how colors, what we perceive as colors, is based in large part about what is reflected. And that leads to our next concept, and that is albedo. And albedo is just the measurement of reflectivity. How reflective is a surface? So, for instance, if light hits a piece of snow, right, a large amount, a high percent of that light is reflected. And that means snow has a high albedo, which means we perceive it as white. If there's dirt and rocks and candy bar wrappers and Chick-fil-A cups in the snow, right, things that aren't as reflective, the snow looks dirtier or browner, right? And so the snow has a lower albedo percentage. It doesn't reflect as much. Generally speaking, things that are lighter colored, closer to white, have a higher albedo percentage, like snow, plain clear water. Things that are dark have a lower albedo, like blacktop, pavement, rocks, dirt. If you look at the Earth as a whole, about 30% is our average albedo, but it varies. Obviously, areas that have a large amount of light covering, so the poles, lots of snow and ice, have a very high albedo. Most of the sunlight that hits the south and north poles is reflected. Not only the sunlight, but also the heat, right? Because if it reflects radiation, like light and also heat, it doesn't get absorbed. It's one of the reasons why the poles stay so cold. The Earth, by the way, really doesn't emit light. It just reflects it or absorbs it. So that's the only reason why we can see the moon from space, or if you're on the moon, you can see the Earth. It's the albedo, actually, the reflection. So this image just shows you that various surfaces have various albedos. Snow has, on average, a reflectivity of 60 to 90%, much higher than bare rock, between 20 to 40. Vegetation has a very low albedo. And think about it. The plants want to absorb that sunlight. That's how they get their food. Dark asphalt. If you ever walked on a street in the summer with no shoes and burnt your feet, that's because the low albedo allows that uh, piece of rock or dirt or street to absorb the light because it's not reflected. So it all varies. And how do we know this? How do we measure this? We can actually use a specific light meter, the same thing that they would use as a photographer, mounted about 5 feet above the ground, just to measure how much light's bouncing back. We can use satellite technology to kind of gauge it as well. And this map just shows you the average albedo of the surface of the Earth, and you can see that it's highest at the poles, it's lowest over the equator and the oceans. Albedo is also part of what we call the urban heat island effect. On the average, cities have low albedos. Concrete, black roofs, less water, less open water because we fill in ponds and lakes and swamps, and we fill them with these, metal dark structures that absorb that light. So if you ever in the summertime, right, you've gone outside in the afternoon, maybe 5 or 6 at night, when the sun is still up, and if you ever walk past a house, you can actually feel sometimes that heat coming from the bricks, or if the sidewalk is so hot. And then later on that evening, when the sun goes down, it's still warm. All of that low albedo environment of a city absorbs that energy and holds it and gradually releases it. That combines with the lack of water. We fill in the rivers, we fill in the swamps, right? There's less evaporation for cooling, and it makes city centers hotter than their rural counterparts. So you look right here at this little diagram, right? In farming areas where there's more open space, less buildings, there's less surface temperature. This right here is a temperature map of Paris taken in the middle of the evening. And you can see the temperature is hottest in the center of the city. Many large cities are easily. Uh, oh, we're going to listen to some music. My son is helping us out in the background. Thank you, Henry. In a little bit later, guy. Many cities are about 5 to 10 degrees warmer at night than the suburbs. And this just kind of goes back to where we talked about the idea of the energy budget and the balance. So the temperature of Earth is based in large part on how much energy we get, how much heat comes into the Earth, and how much is released back into space. So think about it. It's almost kind of like your bank account, right? Money coming in versus money going out, and that's what's left. That's your budget. The technical term is the radiative equilibrium temperature. In other words, let me show you this image. The temperature of this rock is basically a combination of how much energy, heat, shortwave radiation is absorbed during the day versus how much is reflected or released. So it's 5 p.m. This rock has been absorbing energy from the sun all day. If you put your hand on it, it's warmer to the touch than the grass. And that involves the temperature, the radiative heat equilibrium. Now at night, when the sun goes down, we shut off incoming temperature, right? There's no more sunlight. So the rock continues to release its absorbed heat and gradually cools down. And so the radiative equilibrium begins to fall. And if we look at the Earth as a whole, right, of all the energy we get, we absorb about 70% of it, either the ground or the ocean or in the atmosphere, and then 30% is reflected back into space. So that means that we are keeping some of the energy from the sun, and it's how we are not basically a frozen ball of ice. One of the ways this happens is in our atmosphere, right? The Earth absorbs all of the energy, it warms up. Some of that energy is just released right back into the space. Some of it is absorbed by the clouds, and some of it is absorbed by the surface. Then, as things cool and that heat is released, some of it is released back into the atmosphere and stays there. Some of it goes right back out into space. Some of it goes into clouds. But the next thing we're going to talk about is the energy that is kept in the atmosphere, that is absorbed by the atmosphere, and that is the greenhouse effect. So I'm pretty sure everyone in this classroom, and by this classroom I mean where you're watching me on this video, has heard of the greenhouse effect or greenhouse gases or how the greenhouse effect and climate change, right? So first of all, what is the scientific definition? It's basically that process we just talked about where the Earth absorbs heat from the sun. When that heat is released from the surface of the Earth, instead of going back out into space, it is reabsorbed by the atmosphere. And so the atmosphere acts like a blanket, right? Kind of keeps that heat in. And it allows the Earth to remain warmer at night. Because think about it. If there was no greenhouse effect whatsoever, the minute the sun went down, the Earth would freeze at night. It would lose all its energy. It would lose all that heat. There's nothing to keep it there. It's like at night when you go to bed. If you don't have a blanket, you cool off pretty quickly. You need a blanket to keep your body heat on you, keep you warm. If there were no greenhouse gases at all in our atmosphere, so none, the Earth's average temperature would be about 18 degrees. 18 degrees is the same average temperature as the South Pole. So that would mean that on average, the Earth would be one frozen ball of ice. So we need a greenhouse effect, in some effect, to maintain the higher temperatures. And that is a natural process, and that's been going on since we've had an atmosphere. The thing that we talk about in the news all the time, and we're going to talk about maybe in a few chapters, is the anthropogenic greenhouse effect. Or in other words, how we have accelerated and we have increased this to the point where it's now causing massive climate change. So that's the big difference. But it talks to this global heat engine. Because our atmosphere and our Earth stores this heat. Remember we talked about in the very beginning of the chapter, heat wants to even out. Areas of high heat energy, high vibrations, and areas of low, they want to come to the same vibration. They want to transfer the heat. You put your metal spoon in a hot cup of coffee, and it eventually gets hot. They come to an equilibrium. And the same thing happens on the planet Earth. There's more energy absorbed in the equator, the areas that have constant sunlight. That's why they're hotter than the rest of the world. There's less energy at the poles. So we kind of have this imbalance of heat, right? It's hotter at the poles, hotter at the equator, colder at the poles. And one of the things that drives most of the climate on Earth, all of the things we see, is this heat transfer. Heat is transferred. So here's an example. At the equator and 30 degrees north and south, kind of right around the middle of the Earth, right? We actually get a surplus of energy. More energy is absorbed from the sun than is released. So energy heat grows. At the poles, right, less energy is received from the sun. It's colder and more is reflected. So there's a deficit. And so the desire of temperature energy to even basically drives heat from the equator to the poles. And they call this the global heat engine. So what that just means is, and we're going to get into this in the next few chapters, this is the process behind almost all of the major weather patterns that we see, such as hurricanes, tornadoes, thunderstorms. It is the driving factor, this movement of heat throughout the Earth's systems. So we're going to pause right here for our last break. We come back, we're going to finish up with our geographical perspective and the human edge.